Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture. Today we are going to discuss the parameters essential for analyzing machine foundations. Before listing the parameters, let us just visualize the different types of vibrations which a typical block type foundation undergoes. So in general, if we draw the system of axis, we choose the system of axis such that the x and y axis, they are in the horizontal plane and z axis is vertical. Now, under vibrations of the machine, the block undergoes 6 different types of vibrations. The simplest types are the linear vibrations, and here we are first showing the vertical vibrations, which are along the z-axis. Then similar vibrations are also undergone along x and y directions. But the vibrations of x and y directions, they are different from the one in the z direction. The z direction vibration is basically involving compression of soil, and the other two vibrations, namely about x and y axis, they involve shear. Besides these 3 linear vibrations, the block also has possibility of undergoing rotational vibrations about the 3 axes, and they have different technical names. The most obvious is the rotation about y axis, that is the rotation in the xz axis. Basically, this is the main type of rotational vibration, and we call it rocking. So it basically takes place in the plane of the main rotor, and then the vibrations in the plane normal to it, that is the vibrations in the yz plane, they are called as pitching. So these are basically the vibrations about the x-axis. So these involve basically bending of the soil. Finally, the block can also undergo rotation about the vertical axis, the z axis, and these are basically the torsional vibrations, and the technical term used for this is yawing. Hence, altogether there are 6 degrees of freedom for the vibrations of a typical block type foundation. Now let us also list the parameters related to soil, and also the ones related to the block. As far as soil is concerned, we need its stiffness and damping parameters because we model it as a single degree of freedom system. As far as the block is concerned, we need its geometrical parameters. The geometrical parameters are namely the area of the base of the foundation block, the mass moment of inertia, and the area moment of inertia of the base. We have seen how these factors they are used in the calculation of the various stiffnesses associated with the block foundation. Let us now see what types of elastic constants are required for the soil. Now these constants they depend on the type of vibration we are talking about. So there are different constants for compression, shear, bending, and also torsion. So it must be noted that these constants they refer to the dynamic foundation soil interaction. The simplest type of vibrations undergone by the block foundation are the vertical vibrations. Let's say if the block is under pure vertical vibrations, say a reciprocating type machine is operating and there is no eccentricity, then this would generate uniform stresses in the soil below the block foundation, and this would be compressive in nature. So let there be the stress equal to sigma z naught, and that is the amplitude of the stress, and the corresponding displacement amplitude in the vertical direction undergone by the soil, let it be represented by delta naught. So we define an elastic constant of soil Cz. So Z here refers to the fact that the corresponding vibrations are in the Z direction. So this coefficient Cz is called as coefficient of elastic uniform compression of soil. Mathematically, it can be defined as the ratio of the uniform compressive stress acting on the soil, and of course in the Z direction, divided by the induced uniform elastic settlement in the soil below. So here we just make use of the stress sigma z naught and the corresponding deflection delta naught. So the unit of this coefficient shall be kilonewton per meter cube. The next type of elastic constant is that related to horizontal vibrations of the block. So typically, if the block is undergoing horizontal vibrations and we assume that this leads to uniform stresses in the soil, then if the horizontal displacement undergone by the block is delta naught and the corresponding shear stress induced at the interface of the block foundation and the soil is uniform and has a value of tau naught, then we can define an elastic constant C tau which is called as the coefficient of elastic uniform shear as the ratio of the uniform horizontal shear stress acting at the interface of the soil and block to the induced elastic horizontal displacement, which is owing to sliding movement. So here for the present case it will be tau naught divided by delta naught. So again it has unit of kilonewton per cubic meter. Now here there are two possible directions of the soil constant. It could be C tau x or C tau y in accordance with the direction of the linear movement of the block foundation as shown here. If the movement is in the horizontal x direction, then we call as C tau x, and if it's in the horizontal y direction, then we call as C tau y. The next elastic constant pertains to rotational vibrations of the block foundation, that is connected with rocking and pitching. Now under these cases the soil is under bending and hence the stress under the block foundation, which is in the vertical direction, is non-uniform in nature. So basically the block is under a combination of vertical force and a bending moment. So this induces a non-uniform pressure in the soil below the foundation block as shown here. So as a result of these vibrations, the block undergoes rotations as shown here, and here this particular case is that of rocking because it's in the xz plane, and the vibrations are happening about the y-axis. So if the displacement at the extreme right corner is delta naught and the corresponding vertical stress is sigma z naught, then we can define the elastic constant C theta, which is called as the coefficient of elastic non-uniform compression, meaning that it's related to compression but non-uniform, so that induced by a combination of bending moment and vertical direct force. It is basically the ratio of the local compressive stress at the point which we are considering. To the corresponding vertical displacement at the same point. Hence, being non-uniform in nature, we find the stress and the corresponding elastic settlement at some particular point. For example, here we are considering the extreme right point where we have the maximum stress. So for that particular consideration, C theta will be sigma z naught by delta naught. Again, the unit is kilonewton per cubic meter. Now, depending on whether the vibrations are about the y-axis or x-axis, we have two types of elastic constant C theta. It could be C theta x or it could be C theta y. For example, here we are showing two possible scenarios. So if the vibrations are taking place in terms of rotation about the x-axis, so this type of motion is basically pitching. And the corresponding C theta is indicated as C theta x. On the other hand, if the vibrations are in terms of rotation about the y-axis, so this is the main type of rotational vibration and is rocking, and for this case the particular C theta is referred to as C theta y. But essentially the nature of C theta y and C theta x, they are identical. Only difference is plane along which the vibrations are happening or the axis about which the vibrations are happening. The next type of elastic constant we are discussing pertains to non-uniform shear stress. Now, non-uniform shear stress occurs when the block undergoes shearing about the vertical axis, and that is torsion. In technical terms, this is called as yanning. So here the shear stress is induced, but it will be non-uniform in nature. We can understand it by means of the view in the plan as shown here. So typically under torsion type of dynamic force, the foundation block will undergo rotational vibrations about the vertical axis. So at any point the shear stress will be normal to the line joining the point with the center of rotation, and let's say at this particular point, which is the corner, the shear stress is tau naught in the horizontal direction and acting tangentially, and the corresponding horizontal deflection is delta naught. So we define this elastic constant as the coefficient of elastic non-uniform shear, and we use the symbols either C phi or C psi or C theta z. So different books, they are using different nomenclature, but they all essentially mean the same. So this coefficient of non-uniform elastic shear is defined as the ratio of the local non-uniform shear stress acting at a particular point. So here we are considering the point as the corner point as shown here. Divided by the induced elastic horizontal movement at the same point, and of course this would be acting tangentially to the line joining the point with the center of rotation. So this is also a sliding type of movement, but it involves torsion. So now, having learned the basic soil stiffness constants, we can now find expressions for overall stiffness of the soil. So for pure vertical vibrations of the soil, say under a reciprocating type of motion of a machine which is acting concentrically with the base and in the z direction, the soil stiffness can be modeled as a spring acting in the vertical direction. Now this spring constant is represented by symbol Kz, and it can be expressed in terms of Cz as the product of the area of the foundation and the coefficient of elastic uniform shear Cz. Since the unit of Cz is kilonewton per cubic meter and the area unit is meter square, so this makes the unit of Kz as kilonewton per meter. Now, when the block is under the action of horizontal vibrations, that is some kind of reciprocating machine imparting its force in the horizontal direction, and then the soil undergoes shear type of stresses, this interaction between the block and the soil can be represented in terms of a horizontal spring with a spring constant Kx. So this Kx can be expressed in terms of the coefficient of elastic uniform shear. Here, because this is acting in the x direction, we are giving it the symbol k tau x, and this is given by the product of the area of the base of the foundation with c tau x. Similarly, in the other direction, the horizontal vibrations, they can be considered in terms of the spring constant ky acting in the y direction and given by the product of the area of the base to the corresponding coefficient of elastic uniform shear, that is theta y. The next type of stiffness which we will discuss corresponds to the rotational vibrations of the foundation block. Say it could be rocking or pitching. Let's consider rocking first. Let's say the foundation block is undergoing rotational vibrations in the xz plane, that is about the y-axis, and this is basically rocking. The corresponding stiffness constant of soil is in form of k theta y, and this can be considered as a rotational spring as shown here. We denote this spring constant as k theta y. So here y indicates the axis about which the rotations are being considered, and here this is basically rocking. So to derive the relationship of this, to derive an expression for this type of spring constant, we begin with basics. So the basic definition of c theta y is basically as the ratio of the extreme stress to the corresponding vertical deflection, that is sigma naught and delta naught. And then we can make use of Euler bending theory to express sigma naught in terms of the moment acting, that is my by the moment of inertia Iy and multiplied by the distance of the extreme point with regard to the axis of rotation. So here it is a, and further delta naught, that is the vertical deflection at the extreme point, can also be expressed in terms of the rotation theta y as the product of a into theta y. So now this gives rise to a simpler expression, and we can then write an expression for my as the product of c theta y and Iy multiplied by theta y. So now this particular product c theta y into Iy is basically the spring constant, because it's relating to the moment my with the corresponding theta. Hence we can define the spring stiffness, that is the rotational spring stiffness, as the product of c theta y and the corresponding moment of inertia Iy of the base of the foundation. So remember that this particular constant is for the rocking case, that is the vibrations happening about the y-axis. So the unit of this coefficient shall be kilometer meter per radian. Similarly, for the pitching case, we can define the spring constant, and that will be indicated by the symbol k theta x, and it will be given by the product of c theta x and ix. So ix being the corresponding moment of inertia about the x-axis. Having learnt these types of soil stiffnesses, the last type of spring stiffness is that for torsional vibrations, and we call this spring constant as k xi or k phi or k theta z, meaning that it's for the rotation about the z-axis, which is the vertical axis. So as we have indicated, this constant comes into picture because of the torsional moment acting about the vertical axis. So this can be expressed in terms of a rotational spring in the horizontal plane as shown here. So note that this spring is in the horizontal plane, and the corresponding spring constant is indicated by symbol k phi or k xi or k theta z. And as we have learned for the other rotational stiffnesses, this is given by the product of C phi. So C phi is the coefficient of elastic non-uniform shear, and now you can guess which moment of inertia shall come as the product. So this is IZ, and this is basically the polar moment of inertia, and this is the sum of the moment of inertias Ix and Iy, which were used in the case of rocking and pitching. Now, having learnt the elastic constants, let's also list here the various geometrical parameters associated with the block foundation. Now we are not discussing the simpler ones, namely the area and the moment of inertias, but we are straightway coming to the mass moment of inertia. So in general, if we have a finite body and if we have defined an axis about which we want to determine the mass moment of inertia, then essentially the mass moment of inertia, which is represented by the symbol phi, and the corresponding axis, it could be phi x, phi y or phi z, as the volume integration of r square dm. So basically it's the volume integration of r square multiplied by density and the integration with respect to volume. So we can see the closed form expressions for certain shapes. So let's say if we have a cuboid structure, and if the dimensions of the cuboid along x, y and z directions are Lx, Ly and Lz respectively, then we can write following expressions for the mass moment of inertia along the three axes. So here m is the total mass of the block being considered. If we have a cylindrical block, then the expressions for the mass moment of inertia along various axes are as written here. Now this shape is a bit rare in the case of machine foundations. So about the y-axis, which is the longitudinal axis, the expression is m by 8 d to the power 2. Similarly, about the x or y axis, the expression is m by 12 L square plus 3 by 4 of d square. So thank you very much. If you have any questions, you can discuss them during our interaction in the MST.